Okay, this is Mr. Escher. This is Chem 121, and I'm going to go over some few examples of how to work problems from chapter 7, which is stoichiometry and balancing equations, and working through all of that. And so we'll just go through and look at some. And so let me turn on the whiteboard and get my drawing tools. Okay, so there are ways to do it by trial and error. And if the equation is simple, so this would be equation, this would be problem 3, 3D out of chapter 7. And it's Fe solid plus O2 gas goes to Fe2O3 solid. And this, in case you didn't know it, is rust. So this is the rusting of iron. So this stuff here is the red stuff that you'll find on iron. So ferric oxide. So anyway, so now you have to balance this. And this equation is fairly simple, and we can try and do it just sort of by trial and error. And one thing that you can do, you can look at is you could say, well, there's just Fe over this side. So whatever we have over here, we can adjust Fe to make that right. And because oxygen comes in even numbers here, we're going to probably need a multiple of 2 of Fe2O3 to make oxygen right. Follow that logic? That it's oxygen 3, but oxygen comes in 2s over here. So let's try making this 2 Fe2O3, because that'll make us 6 oxygens, right? That'll let us need 6 oxygens. So that would put 3 oxygens over here. And then we'd have 4 irons here. So this becomes 4. So the balanced equation is 4 Fe solid plus 3 O2 gas goes to 2 Fe2O3. And we have 6 oxygens total over here, 6 O's. We have 4 Fe's over here. And over here, we've got 2 times 2 is 4 Fe's. And then we've got 2 times 3 is 6 O's. So everything is balanced, right? And that's a relatively simple one. You can do that sort of just by trial and error by inspection. So let's look at another simple one where we've got, and this would be 3E, which is sodium metal, which is a solid, plus water, liquid, goes to sodium hydroxide, NaOH, plus H2 gas. And this reaction is the one that you see in movies. People will throw a chunk of something in toilets and they blow up a few minutes later, and that's typically what they're throwing into sodium metal. And this reaction generates a lot of heat. The hydrogen will then maybe combust, and the whole thing will blow up. And I'm not recommending you try that. It's actually quite dangerous to do that. But anyway, so if you've actually seen the demonstration, it's very spectacular when these sodium chunks catch fire and then blow up. So again, we can look at this and figure out how we're going to balance this. And one thing we notice over here, again, is we've got an odd number of hydrogens. So we've got 1 hydrogen there and 2 there. So we've got 3 hydrogens here. But the hydrogens over here come in even pairs, right? So again, we're probably going to want to do something over here where we get an even number of hydrogens. So we have an even number of oxygens, right? I mean, even number of hydrogens. So the way to do that, we could multiply everything here by 2, and then we need 6 hydrogens. But we could also just multiply this by 2, the NaOH. So we can make a 2 there, right? So let's write our trial equation down here. And let's just say we've got 2 NaOH. Let's see what happens. All right. So if we have 2 NaOHs there, that means we're going to need 4 hydrogens, right? So that means we're going to need 2 waters over here, right? And now we have 2 NAs here, 2 sodiums. So we're going to need 2 sodiums here. And now to our oxygen balance, well, we have 2 water molecules, so 2 times 1 is 2, and here we have 2 sodium hydroxides, and there's 1, so this is 2. So we've got 2 NAs, we've got 4 H's, and 2 O's, and over here we've got 2 NAs, we've got 2 H's here plus an H2 there, so we've got 4 H's, and then we've got 2 O's, right? Okay. So that one balanced. Okay. And again, it's relatively straightforward. You could do a lot of these just by sort of trial and error. But there's an analytical way to do it. And I've got this in one of the discussion questions, and I'll just run through it here. And I think that's down in the modules. If we looked at the modules, let's see, here we go. So if we looked at module 6, I guess not. Okay. I didn't link to it here. No. Okay. All right. Well, there's a way to do this analytically. And the way that looks is surprised I don't have, because I know I've done this before. Anyway, so let's look at that first example we did before, which was Fe plus O2 gives Fe2O3. And what we can do is we can assign coefficients to these. So we could say that whatever we have, it's going to look like AFE plus BO2 is going to give C Fe2O3, right? And now we can look at how these coefficients are related, right? And we know that whatever A is, whatever number this is, it has to equal 2 times C, right? Because 2 times C is the number of ions in this number of ions here. And so that has to equal the number of ions that went into it. So we know that A is equal to 2C. And we also know that 3 times C is equal to B, is equal to 2B. So 2B is equal to 3C, right? Because 3 times C is the number of oxygens, and 2 times B is the number of oxygens on the left-hand side, right? And so now we could say that, okay, well, so we could say, if we divide through, we could say that C is equal to A divided by 2. And so we can take this and we can plug it into this equation, and we'll have 2B times is equal to 3 times A over 2. And so we're going to have now 4B is equal to 3A, where what I did was I multiplied through this equation by 2, multiplied 2 times 2B is equal to 2 times 3A over 2, and these 2's cancel, and then I'm left with 4B is equal to 3A, okay? So now, I can look at this and I say, okay, well, the only way this is possible, 4B equals 3A, is if B is equal to 3 and A is equal to 4, right? Because then this side, if B is equal to 3 and A is equal to 4, then 4 times 3 is going to equal 3 times 4, right? So we know that A is equal to 4, so we have 4Fe plus, and then 3O2. And now we have to figure out what C is. Well, A is equal to 2 times C, right? So A is equal to 2 times C. Well, A is equal to 4 is equal to 2 times C. So C is equal to 2, right? So this is equal to 2 Fe2O3. And that should be the same, yeah. The same thing we got here, right? But we did this sort of analytically, and we didn't really have to guess at anything. We just sort of went down here and we plugged these coefficients in. And the way this solution, the way this method works, and here's where it's going to get all confused, and it's going to be kind of amusing to watch me try this with a more complicated equation. But let's look at, for example, 3F, which is ammonium NH4 dichromate, Cr2O7. This is a dichromate ion. Goes to chromate or chromium oxide, 3 solid, plus nitrogen gas, plus H2O gas. Oh, I thought that would go to gas. So this is a solid. Okay, so this is a solid decomposition. Okay. So what you can see happen is this nitrogen comes from here, you generate a lot of oxygens, you get some oxygens here. So how does this work? And how do we balance this using this method? Well, let's say that our equation is going to look like A times NH4 7. And I'm going to leave off the little symbols of the phase. And then B times Cr2O3 plus C times N2 plus D times H2O. And now we can look at these and we can say that 2 times A has to equal 2 times B, right? Because there's 2 chromiums here and there's 2 chromiums there. So however many we have of B's, however many of these we produce, we have to use the same number of these because we're going to get 2 chromiums here and we're going to use up 2 chromiums. So this might be a 6, might be a 5, could be a 2, could be a 1, but that number has to be the same because we have to balance the number of chromiums. That's the only 2 places we use chromiums. So we know that A equals B. Okay. And now we can look at relationships between C. Well, this is the only place where nitrogen is used, right? Right. And so we get 2 nitrogens for each C. And over here, there are 2 NH4s. So there's 1 nitrogen and NH4. So there are 2 nitrogens in each ammonium dichromate. So that means also that A has to equal C, right? And now for D, we know that for D, we have oxygens. We can write 2 equations for D, one for oxygen and then one for hydrogen, right? So let's look at oxygen first. We have, or let's look at hydrogen first, right? Because we have, this is the only place that hydrogen appears over on this side, right? Whoops. So hydrogen only appears here in this term here, and we get 2 hydrogens for each water molecule for each D, right? So that we know on one side we have 2 times D, and now, so this was for chromium, and this is for oxygen? No, for nitrogen, right? And now we're doing hydrogen, right? And then we'll come up with an equation for oxygen in just a second, right? So here's our hydrogens here, and we get 2 for each D. And what's over here, we have 2 times 4 is 8. So we get 8A is equal to 2D. And we're just going to write that for simplicity's sake, is that 4A is equal to D, right? Because I can just divide through each time. And this is our hydrogen equation. 4A is equal to D. Now we can also write an equation for oxygen, where here on the left side, we're going to get 7 times A. And that's going to equal, there's a 3 here, B, 3 times B plus, and then D, right? And so now we've got this set of equations. A equals B, A equals C, 4A equals D, and then 7A is equal to 3B plus D, okay? And so now we can start to make substitutions, and hopefully we're going to come up with a sensible answer. We should be able to. Okay, so A equals B and A equals C. So we know that this here is let's see, how are we going to do this? A equals B, B equals C. Oh, well, if A equals B equals C, right? Because this means that A equals B equals C. That means that this coefficient, and this coefficient are all the same. And that means that, this is 4 times whatever this is, right? It's because 4A is equal to D. And that means that 4A is also equal to B, and 4A is also equal to C, right? Okay, so we can plug that in anywhere here. And so now it becomes sort of a logic problem. We have A equals B equals C. We could say, well, okay, what if A is equal to 1? And then we have NH4 to Cr2O7 goes to Cr2O3 plus N2 plus, and now 4 times 1 is 4H2O. And does everything balance? We have 8 hydrogens over here, 2 times 4. We have 2 chromiums, 2 Cr. We've got 2 nitrogens, and we've got 7 Os. And that's over on this side. And over on this side, we've got 4 times there, we've got 8 hydrogens. We have 2 chromiums. We have 3 oxygens from there, plus 4 oxygens from there. So we have 7 oxygens, and we have 2 nitrogens. So it balances. So what we did here was we solved this equation, and we saw that A equals B equals C, which meant that all of these coefficients were the same, and that D was equal to 4 times that. So that means that what we could do is we just pick the lowest common denominator here, try 1, and then plug it in and see if it worked. We could have taken 2 here, and then everything would have been doubled. This would have been 2, and then 2. This would have been a 2. This would have been a 2. This would have been a 2, and this would have been an 8, and that's still a balanced equation, right? And we could choose any integer here for A, B, or C and plug that in and get this to balance. But that's sort of, if you do it this way, if you set it up like this, you'll always be able to balance it. Although it is a little bit of work in solving a couple equations. I'll do one more example like that, and you can maybe see that it's either not worth your time or so let's say that we have H2 plus I2 is equal to HI, right? And so, I mean, we could do this by inspection, and we know this is H2 plus I2 has to go to 2HI, right? Just by inspection, because 2 H's here, 2 I's here, balance that. But if we did it the other way, we'd have A H2 plus B I2 is equal to CHI. And we would know that 2A has to equal C and 2B has to equal C. So that 2A has to equal 2B, or A has to equal B, right? And so if A equals B, let's try A equals 1 equals B. And so then we would have H2 plus I2, and then C would equal 2 times B and 2HI. See, that's how it works. And it can be quite useful for really, really complicated equations. And let me see if I can find another one that we didn't, it's not on the problem set. Where's my cursor? There it is. Okay, I signed 4G. Okay, let's look at 4A. We'll do one more. So this is 4A. And this is silver plus hydrogen sulfide, which is the smell of rotten eggs, in case you didn't know, plus oxygen, goes to silver sulfide plus H2O. And this is the black you'll find on silver. This is tarnished silver, is silver sulfide in general. Okay, so let's say that, so our balanced equation is going to be A times AG plus little b times H2S plus C times O2 is going to go to D times AGS plus E times H2O, right? And we can see right away that this D has to equal A because there's only one A. There's only one place that uses silver. So we know that A equals D. And we also know that there's one sulfur over here and there's one sulfur over here. So B also has to equal D. So A equals B equals D so far. And we also know that 2C has to equal E, so that 2C has to equal E, right? Because there's one oxygen, right? And we also have to know that B has to equal E because there are two hydrogens here and there's two hydrogens here. So this is for silver. You're going to get one equation for each atom, right? This equation here was for sulfur. This equation here, 2C equals E, is for oxygen. And this equation here was for hydrogen, B equals E. And there's 4 different types of atoms, and you're going to get one equation for each type of atom. I should have mentioned that before. For each type of atom in this, you get one of these equations, one of these linear equations, right? So we know that A equals D, B equals D, and B equals E. So we also know that because A equals D, and that also equals B, but B equals E equals E. So A equals D equals B equals E. And then 2C is equal to E, right? Well, let's just set A equals B equals D equals E equal to 1, right? And that would make 2 times C equals to 1, which would mean C would have to be equal to 1/2, but we know that can't be, right? Because we can't have half fractions. So let's double it and let's make all of these. See how I did that? See how I saw that? I set them all equal to 1 just to begin with because they're all the same. And then I looked at my equation for oxygen, which is 2 times C equals E. Well, if E equals 1, right? 2C equals 1, then by dividing through each side by 2, this is an E, right? Then I'm going to get C is equal to 1/2. But I know I can't have fractional coefficients out here, right? It has to be an integer. So I know that this can't be right. So this isn't right. So 1 isn't right here. So I go back and I'll say, okay, well, I know that 1 isn't right. Let's try 2. What happens if this becomes 2? Okay. And then we have 2 times C is equal to 2, and C is equal to 1. Okay. So that means our equation is 2 silver, 2 Ag, plus 2 H2S, plus O2, C is equal to 1, C is equal to 1, goes to D is equal to 2 as well, 2 AGS, plus and then E is equal to 2H2O. Does that balance? Over here, we've got 2Ag, 4H, 2S, and 2O. And over here, we've got 2Ag, 4H, 2S, and 2O. Whoops, it's just an O, right? So it balances. So this is the balanced equation. And it's maybe a little less work. It's a little less trial and error, excuse me, to do it this way. I don't know. If you get the hang of it, it can be more convenient to do complicated equations like this. But if you don't want to use it, that's fine. Anyway, so that's that. Now let's move on to the second class of problems. Let's see, 6A, 13A, 13D. Where were those? 6 was balanced equations. It's more balanced equations. Okay, classifying chemical reactions. This one seems to get people because people get into these funny things of substitution reactions and replacement reactions and all of that. And these are subclasses. And as far as the book is concerned, and as far as this course is concerned, there are 3 types of reactions. 1, there are acid-base reactions. And I'll go through and describe how each of these differs. 2, there are reduction oxidation reactions. And 3, there are precipitation reactions where a solid is formed. Okay, so how are these different? And so there is no such thing purely as a substitution reaction. It is an acid-base substitution reaction, it is a reduction oxidation substitution reaction, or it's a precipitation substitution reaction, right? So when you're doing these assignments, don't put down it is just substitution. Figure out what in these classes is going on. Okay, so what are these classes? How do they work? Acid-base. As far as this course is concerned, we're going to use the Bronsted-Lowry definition of acid-base. We'll get to that in a later chapter. You don't have to worry about this, Lowry. And that involves transfer of H plus or OH from one molecule to another. Another way to think of it is an acid plus a base come together to form a salt plus water. And you go, huh? Okay, so how does that work? The canonical acid-base reaction is hydrochloric acid, HCl, in a liquid, or aqueous phase, sorry. Aqueous phase, plus sodium hydroxide, also in the aqueous phase. So these are 2 things that are dissolved in water, and they combine to form NaCl, table salt, plus H2O. So the H from here combines with the OH from there, and that's how you get the H2O. And then the Na from there combines with the Cl, you get the salt, okay? That is classic acid-base reaction. Acid, base goes to salt, water, okay? So if you see something like, here, did we do C? Let me look. No. So this one, Al, OH3, aqueous, plus 3HCl, also aqueous, goes to AlCl3 plus 3H2O. Base, acid, salt, water. Right? Okay. Pretty easy to spot acid-base reactions if you know what you're looking at. Okay. You have to produce a salt and you have to produce a water. There's one in there in the problems that I assign where it doesn't produce salt and water. An acid's involved, but it's not producing salt and water. So be aware of that. Has to produce a salt, has to produce water, and it has to have a base and an acid. You can't just have a base on one side and on the other. Okay. So here's another example of an acid base from problem sets. We have calcium hydroxide, aqueous, plus hydrobromic acid, also aqueous, goes to calcium bromide plus 2H2O. Salt, water, base, acid. Acid base, always acid base produces salt water. Look for that, okay? That's an acid base reaction. Okay, so what's a redox reaction? Reduction oxidation reaction. That's one where the charge on atoms change. Sort of that's how you look for it. You look for charge on atoms change. And what that means is there was transfer of electrons. Reduction is gain of electrons. Oxidation is loss of electrons. Reduction oxidation means the transfer of electrons. Electrons are moving from one atom to another. And it can have a lot of different looks to it. But a lot of reactions, or most reactions that you see, will be reduction oxidation reactions. This is the way it goes. And so let's look at a fairly simple one. H2O plus carbon as a solid goes to CO gas plus H2. And this is an important reaction. I can't remember exactly what it's called, but this is one of the ones where you produce hydrogen gas for energy storage. Anyway, so what's going on here? All right. And so let's look at what happened. Well, over here in the water molecule, H is +1, right? And oxygen is 2-. Carbon is 0. It's neutral because it's in a solid. And what happened over here? Well, carbon now is +2 because oxygen always stays at 2-. So I'm sorry. Wrote that the wrong way, is 2+ because oxygen is always 2-. Oxygen is always 2-. So carbon was 0, went to 2+, and hydrogen went to 0. So hydrogen gained an electron. So we had H+ plus E- goes to H0, and carbon went from 0 to carbon 2+ plus 2 electrons, right? Because it became a doubly charged thing, so it had to lose 2 electrons. So here is reduction, and here is oxidation. So this is reduction, and this is oxidation, right? So this reaction here is reduction oxidation, or redox. Right, so you'll hear me say redox, and that's what I'm talking about, reduction oxidation. Transfer of electrons, really simple concept. Transferring electrons from from one atom to another, it's kind of hard to spot sometimes because they get sort of they can be hidden. And so you have to sort of look and figure out what the heck is going on. So here's a good one that is sort of flies under the radar. Okay. Oops. Really, I gotta up my game and drawing on a tablet. Okay. So calcium, solid, plus bromine, liquid, Br2, goes to CaBr2. What is that? Is that acid base? Well, there's no acid and there's no base, right? There's no precipitation, so to speak. This is a solid, this is a solid, and this is a liquid. So let's look and see if things change their ionization state. Well, over here we had calcium is 0 because it's in its, right, it's 0. And bromine is in its elemental state, so it's also 0. But over here, calcium went to +2, and bromine went to -1, 1 minus, right? So that means that bromine gained an electron to become bromide, and calcium lost 2 electrons right? So calcium was oxidized, bromine was reduced. And calcium is the reductant and bromine is the oxidant, right? That's how you would think about it. So bromine was reduced, calcium was oxidized. This is the oxidant, meaning it's the thing that encourages other things to give up electrons. And bromine is the reductant, is a thing, calcium is the reductant, the thing that forces other things to accept electrons, right? So once you know what to look for, reduction oxidation reactions are relatively easy to spot. They're not, they are easy to see, and so don't get confused by them because they're ubiquitous, they're everywhere, and the vast majority of reactions you'll see are going to be reduction oxidation reactions. Okay, so let's see, which two did I assign there? 13A and 14D. 13A and 14D. Oh, I went through and gave you the answer. All right, well, so you all got the answer now. Great, way to go. I'm going to do one more and then we'll move on. So one more oxidation reduction reaction. So let's do it. C6H12 liquid plus 9O2 gas phase goes to 6CO2 gas plus 6H2O gas. So this is the oxidation of hexane. Hexene. Hexene. Okay. So this is hexene, not hexane. Not that that matters. But anyway, so let's look at what happens here. Well, over here we have C6H12, and over here we have 9O2. Well, O here is 0. And then carbon in this one is going to be +4, I think. Carbon here, I think, formally goes as +4, and hydrogen will go as -1. Is that how that works? All right, well, let's go on. We figure it out from over here because we know that oxygen over here goes to -2, and oxygen here goes to -2, right? So that the carbon here has to become +2, and the hydrogen here has to become +1. 1 positive. Is that going to work? So the oxygens are acquiring a bunch of electrons. So oxygen 0 plus 2E minus is going to give us O2 minus. So that makes sense. So what gave up electrons? Oh, I'm sorry, we have to balance this guy. So our carbon has to be +2 here. +2, I'm sorry, I'm not used to working with these. Carbon has to be +2 because you're going to get 12 negatives. This whole thing, C6H12, has to have 0 charge, right? And so if carbon is +2, then you get 12, or you get 2 times 6. 2 times 6 is +12 from the carbons. And then if hydrogen is -1, you get 12 negatives there, right? Okay. So the hydrogen negative went to hydrogen positive plus 2 electrons. So for each hydrogen that goes to a for each hydrogen that gives that goes from H minus over here to H plus, it's going to give up 2 electrons. So that means that there was, and because there's 12 electrons, 12 hydrogens, there were 24 electrons that were produced by hydrogen getting oxidized. And now we better have 24 electrons that are going to get taken up by carbon. Let's see. Each one of these is going to be 2, so that's 18. So that's not working. So what did I do wrong? Oh, I made it way too complicated. All right. So clear all drawings. Okay, this is what you think about this one. Sorry. We have C6H12 going plus, what is it? 902. And it goes to 6CO2 plus 6H2O. Okay. So this is covalent. This is elemental. This is covalent, and this is water. So the formal charge on carbon and hydrogen here is both 0. So carbon is 0, hydrogen is 0, and here oxygen is 0 as well. And this is covalent as well. So the formal charge on carbon is still 0, and on oxygen is still 0. And over here, the formal charge on hydrogen is +1, and the formal charge on oxygen is 2 minus, right? So what happened is we have 6 oxygens going from 2 minus. So oxygen was the thing that got reduced, went to, plus 2 electrons went to O2 minus. And then we have hydrogen 0, oxygen 0, went to hydrogen plus an electron. Okay, so over here we have 12 hydrogen going to 12H plus 12E minus. And over here we had 6 oxygen plus 12E minus going to 6O2 minus. And so these 12 hydrogen plus and these 6 oxygen 2 minus combine to make 6 water molecules. And then the other 12 oxygens combined with the oxygens. And so that this is the redox pair from this equation is the hydrogens from the hexene lost electrons, the oxygens, some of the oxygens from these oxygen molecules gained electrons, and then the other ones just rearranged and formed covalent bonds with the carbon dioxide. I'm sorry. Sorry for not thinking that one through correctly at first, but this is how you would think about this, and this is the redox pair here for that reaction, right? So if you look, even if you do a ham-headed job at it, and remember that for covalent compounds like this, there aren't formal charges, there's zeros, then you can find the things that get oxidized on the other side. And remember that this is the one where you'll have formal charges and not this one. Okay, so that's the other example of redox reactions. Now the other class of reactions is precipitation. And precipitation are ones where a solid forms. Okay. So there are a couple in here that are shown to be precipitation, but for example, if you had this reaction where you had trying to think of one that is I know to be a precipitation reaction. So let's try oh, here's a good one. So we have AgNO3, which is silver nitrate, plus HCl, which is an acid. That's going to go to, and this is in aqueous phase, and this is aqueous, meaning they're dissolved in water. And this is going to go to AgCl, and this might be 2. Silver is +2, I think. So this is Ag2, AgCl2, and this is 2HCl, plus 2HNO3. Okay, and this is a solid, right? So it forms a solid, meaning that when you mix these two things together, all of a sudden there's a solid. It precipitates. It's a precipitant. We formed a solid all of a sudden where there wasn't one. So that's a precipitation reaction. And you might think this is an acid-base reaction because we've got an acid here that's combining with something, but we've got an acid here and we've still got an acid over here. So there wasn't an acid-base reaction because there's no base. What we did is we combined this Cl here with this Ag and formed a solid. So that's a precipitation reaction. And they're separate from oxidation and acid-base reactions. So be aware of that. And they can look like, you know, there's some class of substitution or transfer or whatever they're called, but it's really a precipitation reaction. So look for that. If on one side, if on the product side there's a little s, then it formed a solid. And that's a key, that's a precipitation reaction. Now, there are acid-base reactions that precipitate. For example, the classic one is in the gas phase, you'll have HCl gas plus NH3 I'm sorry, NH oh yeah, this is precipitation reaction. Okay, NH3 gas, and that's going to form NH4Cl solid. And so this is kind of an interesting demonstration. You take a bottle of HCl and a bottle of ammonia, and you blow across the top and you form these big white clouds of ammonium chloride. And this is a precipitation, but it's actually an acid base because here's the acid and here's the base. And you're neutralizing to form a salt. But there's no water involved in this one because it's happening in the gas phase. But this is an odd acid-base gas phase precipitation reaction. So I wouldn't use that as an example or anything. Be aware sometimes you can form a solid and it's still an acid-base reaction. But anyway, in general, what you're going to see is these precipitation reactions where you have a salt and another salt that's soluble, and it's going to form an insoluble salt and then some other soluble salt, right? So be aware of that. That's precipitation. So those are the three kind of reactions. And I think, let's see, what else was there in these? Classifying chemical reactions, and then there was some stoichiometry stuff we did, right? So let's look farther down. Classifying chemical reactions, reaction stoichiometry. Okay, let's do a couple of these examples. 42A is what? Okay, right. This one seemed to get people too. So let's do what? That's not what I wanted to do. There. Okay. So 42A asked you to calculate the number of moles and mass of chlorine required to react with 10 grams of sodium metal to produce sodium chloride. So let's do let's do 42C, which says the number of moles and the mass of sodium nitrite required to produce 128 grams of oxygen. So we need to know mass of NaNO3, sodium nitrite, required to produce 128 grams of O2. Okay, well, first thing we need to do is we need to write down the equation. So we know we've got NaNO3 here, and this is going to decompose somehow. And one of our products is going to be O2, which is what we want, O2 gas. And then they tell us the other product is NaNO2. So now we have to balance this equation. Well, we can look at this and just think, okay, we're going to need at least two of these because we're going to pull an oxygen atom off each one of these. And then we're going to get two of these and one O2. So over here, we've got 6 oxygens. And over here, we've got 2 times plus 4 is 6. 2 sodiums, 2 nitrogens, 2 nitrogens. So this is our equation. 2 NaNO3 goes to 1 O2 gas plus 2 NaNO2. Okay. So this is our balanced equation. And we want to know the mass of this stuff required to produce 128 grams of this stuff. Well, the molecular weight of oxygen gas, O2, is 32 grams per mole. Molecular mass is 32 grams per mole. That means in 128 grams, so 128 grams divided by 32 grams per mole gives us 128 divided by 32 grams multiplied by moles per gram. Remember, because this flips over, grams cancel, and this comes out to be, I think, 4 moles. Hopefully you see how I did that. So this means that I produced 4 moles of O2. And now produce 4 moles, it's a 2-to-1 ratio. If I have 4 moles here, that means I had to use twice as much. So this is 8 moles of NaNO3. So what mass do I need? Well, now I have to calculate the mass, the molecular mass of NaNO3. And so I know that sodium is 23 grams per mole. I know that nitrogen is 14 grams per mole. At least I think sodium is 14. And then I know that oxygen is 3 times 16 grams per mole. So then, because I'm not going to be able to do that in my head, I've got to find my calculator, which I'm in this place somewhere. The keyboard. So 3 times 16 is 48. So 48 plus 14 plus 23. So this is 85 grams per mole. So the mass is 4 times 85 grams per mole. 4 moles times that is 340 grams. So I need 340 grams to produce of NaNO3 to produce 128 grams of O2. And let's see, I guess I better pull up the answer key since I didn't do this ahead of time and make sure I did this right, just so that I can feel good about showing you the right way to do it. So let me find that answer key on my hard drive. And I should bring this in front of for hard time. Let's see, chemistry. There they are. Solutions, structure manuals. We'll get to chapter 7. And this is section 3. And I'm looking up 42C. 42C. All right, 43C. Let's see. Two moles required to produce 1 mole of oxygen. Oh, I multiplied by the wrong number. I multiplied by 4. I need to multiply by 8. I'm so stupid. Okay, so this should be 8, and this will come out to be double this, which is 680. Great, 680. All right, so demonstrating that I can make stupid mistakes too. So 8 times 85 is the answer, because we have, if we use 4 moles of oxygen, we're going to need 8 moles of NaNO2, sodium nitrate. So we're going to need 8 times the molecular weight, which is 680 grams. So let's do one more where I'll try not to screw it up, and then I'll do this again. So let's do 42 and 43. This is 42 and 43 D, which is moles and mass of CO2 formed by combusting 20 kilograms of carbon in an excess of oxygen. So we're going to have carbon solid plus O2 is going to go to CO2. So we don't know what this is, but we've got a lot of it. But we know that it's 1-to-1, right? That for each mole of carbon we burn, we're going to get 1 mole of CO2. So 20 kilograms, carbon weighs 12 grams per mole. So we have 20 times 10 to the third, because this is, now let me write this out for you. So we have 20 kilograms times 10 to the third, 1,000 grams per kilogram. That's how many grams of carbon we have, divided by 12 grams per mole. So this is the atomic mass of carbon. This is the mass of carbon we started with. This is the conversion between kilograms and grams. So we're going to get 2 times 10 to the 4th, where this, I move this over 1 to the left and added 1 to there, grams, divided by 12 grams per mole. And so 2. And so this is equal to 1.667 times 10 to the 3rd moles of CO2 produced, because we used 10 to the 1.667. We started with 1.66 times 1,667 moles of C, and we have to get 1 to 1, so we get 1,667 moles of carbon, and then we multiply that by 12. I'm sorry, we have to multiply that by the molecular weight of carbon dioxide, which is CO2 is 12 plus 2 times 16, which is equal to 44 grams per mole. So we multiply that by 44, and we come out with 77.3333 times 10 to the 4th, or 73.3 kilograms CO2. And hopefully I did that right. Yes, I did. So this is the right answer. I got that right for a change. Okay. So that's how you do this reaction stoichiometry ones. Is first thing you have to do is you have to write out the equation, balance it, and figure out what the proportionality is between reactants and products that you're interested in. Okay. It's relatively straightforward, but you do have to write down the equation and balance it, and then you'll be able to do it. So let's see, what are the other ones I assigned? Let's see, I assigned 57, 64, 87. All right. So I assigned 57. So let's do 56, just to prove that I can sort of do these. So 56 is what volume of 0.750 molar HCl, hydrochloric acid, can be produced from HCl produced by reaction of 25.0 grams of NaCl with H2SO4, sulfuric acid. Okay. So what's our reaction? We have HCl aqueous plus H2SO4. Right? I'm sorry, NaCl. This is NaCl over here. And this is going to go to HCl plus Na2SO4. And so now we have to balance this equation because it's not balanced right now, right? And so probably what we're going to need is we got 2 H's there. So let's try 2 here, and then we're going to form 2 of those. And this should work out. We've got 2 sodiums here, 2 sodiums here, 1 SO4 here, 1 SO4 here, 2 Cl's, 2 Cl's. Okay. So that means it's 1-to-1 between NaCl and HCl, right? For each mole, for every 2 moles of NaCl we react, we get 2 moles of HCl, right? So for every mole of NaCl react, we're going to get 1 mole out. So now let's look at the molecular weight of NaCl. Well, NaCl is going to equal 23, which is the molecular weight of sulfur, plus, sodium, plus 35.5, which is the molecular weight of chlorine. So this is 58.5 grams per mole molecular mass, right? And we had 25 grams of NaCl to start with. So that means the number of moles of NaCl is equal to 25 grams divided by 58.5 grams per mole, which is 25 divided by 58.5 is 0.427 moles of NaCl. So that means we have 0.427 moles of HCl, right? And now we're going to produce 0.750 molar solution, and we need to know the volume. So we know that this has to equal whatever volume V we have times the concentration, which is 0.750 moles per liter. See how I did that? That I know this concentration I'm going to come up with is 0.75. The thing I want to know is the number of volume, right? So however many moles are in this volume 0.75, that has to equal the number of moles I started with, which is 0.425. So that V is equal to 0.427 moles divided by 0.750, I should make this a times symbol, moles per liter. See, and this is going to flip around, right? So this is equal to 0.427 over 0.750. And then we have moles per liter over moles. Moles go away and we're left with liters. So 0.427 divided by 0.750. And we come out with, I can make 0.570 liters of solution. And now the moment of truth, we'll go down and check the answer key, but I think I have to, all right, that's going to be in this one. Hopefully I did this right. And the answer is actually 0.570 liters of solution. Okay. So the key steps here are balancing this equation, recognizing what you're trying to find, calculating the number of moles here, and then remembering how you figure out how you set up the final step of the problem, which is going from volume and concentration back to the number of moles, right? So that the volume is the unknown. If you multiply volume times the known concentration, you should get out the number of moles to start with. Okay. Relatively straightforward. Okay, the last thing that I assigned was some problems on reaction yields. And I think I did one problem on reaction yields. So let's look at a couple of reaction yield problems, and then I'm going to stop because this has gone on for a while and probably everybody's pretty bored. 6487, 64. So all right. Excuse me. Oh, 87 is quantitative chemical analysis. So let's look at some of those. What was 87? All right. So 87 was what volume of 0.6 molar NaCl? All right. So let's look at that instead. And let's, that's in 7.5. So let me open that up just to get prepared. 7.5. Perfect. Okay. So, and I assigned 87? Yes, 87. All right. So I assigned 87, which you have the answer in. So let's look at one that I don't have the answer, that isn't in the back of the book. So let's look at 88. And in 88, it is what volume of 0.08892 molar HNO3 is required to react completely with 0.2352 grams of KH4 K2 PH4 potassium hydrogen phosphate. Okay, all right. And so they give you the reaction, and it is 2 HNO3, which is nitric acid, plus K2HPO4, and it goes to H3PO4 plus 2KNO3. And this doesn't look like it, but it is an acid-base reaction. And so what's happening here is you've got an acid here, and this is a base, and this is a salt you're producing, and this is another acid that gets produced in the same way, but this is the acid base, all right? So so let's look at this. So we want to know the volume of 0.008892 is required to react completely with 0.235. Okay, so now we have to figure out what the molecular mass of this is, because we know that whatever this is, we need 2 moles of nitric acid to react with 1 mole of this. So for every mole of this, every mole of potassium hydrogen phosphate, we need 2 moles of nitric acid to do the reaction. So first thing we have to do is we have to get the molecular mass of potassium hydrogen phosphate, and hopefully one of you knows that off the top of your head, because I sure don't. So let's see. I think the molecular weight of potassium hydrogen phosphate is molecular mass is 174.2 grams per mole. All right. So now we can figure out how many moles of potassium hydrogen phosphate we need. So we need 0.2352 grams divided by 174.2 grams per mole. And that's going to give us 0.2352, 174.2. And this is 1.3502 times 10 to the minus 3 moles of K2HPO4. We get a sense that this is correct. Potassium is, there's 4 oxygens, which is 64. One for that. Phosphorus is something or other. That looks about right. So we'll take that as a, sorry. So there's 1.3502, which means we need double of this. We need 2 times that. So we need 2 times 1.3502 times 10 to the minus 3 moles of HNO3, which is equal to 2.7003 times 10 to the minus 3 moles of HNO3, right? And the same thing before, we've got 0.00892, right, molar HNO3. So the volume times 0.08892 has to equal 2.7003 times 10 to the minus 3, or V in liters is equal to 2.7003 times 10 to the minus 3 divided by 0.08892, which is equal to 0.08892. So we need 3.037 times 10 to the minus 2 liters, which is equal to about 30 milliliters, or 30.4 milliliters. Yep, and this is the answer, 30.37 milliliters. Okay. So that's how you do these. Again, you set up the equation, you look at what your molar ratios are. They're not fiendishly complicated in terms of the math, but they do take a few steps, and working through them like this, you can sort of see what's going on. And then there's remembering how you convert between concentration, number of moles in solution, and volume. You have to remember that. I'm going to stop there because this got way longer than I meant it to be. Hopefully you'll find these a little bit of use, and I will talk to you later.